Hello guys, Sir DV again here to continue my lecture on deformation of string. So last time what we derived are terms in terms of displacement and deformation. So today we will be talking more about that, starting from this figure upon which the particle motion p to p prime is extended in terms of the differential motions. And so if you are to consider now a differential u in terms of this, okay? So our original vectorial representation is given by this triangle here, and let's try to extend it further into placing some differential displacement in the material and in the spatial coordinates, or simply the Lagrangian and the Eulerian description. Okay, so this becomes now the new vectorial, okay, triangle, which is simply given by your P, Q prime, and let's say there's a point here, O, okay? So this POQ prime here represents the differential vectorial motions in terms of the Eulerian, Lagrangian, and the resulting differential displacement du, where differential displacement here du can actually be assumed to be the length traveled from P to P prime, okay? Sorry, this is P to O to P prime, or rather O to Q prime. So this is the one that we are referring to here, okay? So this travel, since your P to P prime is given in terms of S, the arc length, the length traveled, okay? So this is from P to P prime there. The motion of the particle, since it is a combination of both displacement, translation and displacement, plus rotation, rather. So we'll tend to be forming an arc, okay? So this is actually an arc travel. It's not a straight line, okay? So this could travel in an arc there. So as true with your differential u here, it can travel in terms of a very small arc. And since we are talking of very small deformations, then these two here are assumed to be equivalent. So let us now define the length of the arc ds, which is the same as the differential du a while ago, to be the length of arc traveled again, this is from particle O to Q prime. Okay, this refers to particle S. So ds is du, while this s is equal to u. Okay, so we say that the square of the length ds is given by the simple vectorial notation. Okay, so these are vectors. Since we are talking here of your differential x capital, and this is dx, and this is ds, then your ds is okay, your dx squared is simply equal to dx squared plus ds squared. So this will form an equation in terms of a ds squared is equal to dx squared minus dx, capital Dx, or d capital X squared, and evaluating dx in terms of an initial notation. Remember what I told you, that there's no such thing as a dxi squared, so we have to place it in juxtaposition in this manner. So dxi such that if I make use of a chain rule, okay, so the chain rule implies that the derivative or the differential, the total differential dxi is simply equal to the partial derivative of xi over xj dxj. Okay, so this is actually simplified in terms of contraction, so you will lead to an equation in the form of dxi is simply the partial derivative of dxi. Okay. So equation 3.1.2 may now become this, as we use the dxi term by substituting, of course, this value here obtained from the chain rule. Note that the change of the dummy index in I to k at the right hand side to avoid confusion. No? So I just change the i's to k's, so it doesn't change anything, because this is a summation. It can contract into a scalar, okay, a value. Okay, so there's no restriction at whatever index I use here. So this will also be a scalar value here. Okay, so this now becomes this, and it is through substitution. Okay, so the Kronecker delta is used here as a substitution operator. So I hope you have answered this correctly on your quiz. So substitution operator, if you want to change a dx capital J to a d capital Xj to a d capital Xi, you just multiply it by a delta Ji, and substituting it here, so we just place it there, will yield to this equation here. Okay, and take note that we already have defined this value in the previous lecture, and this is simply f. Okay, and also this one here will be your F transpose. Okay, so this will contract into a J, so this will be a capital DX J dxj will yield this part here. Okay, this is now this part here. Okay, and your F transpose and F will simply be this part here and this part here. Okay, so there's a little bit of inconsistency such that this value here should not be changed in terms of so the missing step here is you have to multiply this by a delta jk all over delta kj. Okay, so to make this a transpose, so this must be substituted by a j here, such that this will result to a partial derivative of xj with respect to capital X. Okay, so kj and jk will yield to an F transpose F in this regard. So similar procedures will yield to obtaining the Eulerian description. So our first derivation here, Lagrangian description, so similar process will yield to this one. Okay, so what will only change is of course the position of the capital X and the small letter x there, such that this becomes simply, we know that this is the inverse, F is the inverse. Okay, F is equal to h to the negative 1. So this simply becomes dx h transpose h dx. And going back to the original equation before, okay, so this is now your ds squared is equal to d small x minus d capital X. So this is now r. Okay, substitution for dxi dxi, and simplifying further, factoring, we get this. Taking note that what we are interested on is this factor F transpose F minus 1 and this factor 1 minus H transpose H, which are defined to be the Green deformation tensor and the Cauchy deformation tensor in terms of, again, the Lagrangian and the Eulerian. Okay, for the finite strain tensor, Okay, so these are deformation tensors. So we have already described the material gradients. Okay, so this is now the gradient, the deformation gradient, the displacement gradient, and now we have the deformation tensor. So we have the deformation tensor, and we also have here our finite strain tensor. So these are the terms we have to uh, understand, no, to make use of it later in our application concerning deformation string problems. Okay, for the finite string tensor, all we need to do is to take 1/2 of the green deformation tensor. Okay, so 1/2. So we get now, we know that f is j plus 1, so that this becomes a j plus 1 transpose plus a j plus 1 minus 1. And we take note that in the property of a matrix is that j plus 1, this is an identity matrix, is simply equivalent to a j transpose plus 1. Okay, so just like distributing here, so j transpose 1 transpose is 1, such that if we place it here and multiply, okay, so this becomes now a j transpose times j is j transpose j, okay, and j transpose times 1 is j, and 1 times j is so let's have it clearer here, so to avoid confusion. So let's try to multiply now a j transpose plus 1 multiplied by j plus 1. Okay, so if I placed these two first, I get j transpose j. If I place this and that, I get j transpose. If I place this, I get a plus j. Okay, and this is 1. Okay, so this is the correct, no, distribution, but I have a negative 1 here, so if I subtract 1 there, this will cancel. So what will yield the final result is a j transpose plus j transpose j. Okay, so which is simply equivalent to defining again what is j. J is simply the displacement gradient in the material. Okay, so j is the material displacement gradient. Okay, in terms. So when you say gradient, it's simply a slope. Okay, so this is just a derivative. So it's a partial derivative of the displacement with respect to capital Xj, because we are referring here to the Lagrangian description. Okay, so material means this is a Lagrangian description. So with this, since this is transposed, this must be interchanged. Ij, this must be a Ji, and then again plus J transpose. Okay, so I use a different UK XI here just to be more precise, or para hindi siya confusing, no? Because if I use an IJ and a JI there, so there will have been some confusion on the definition of a repeated index. So I use a KI and a KJ. Okay, so the repetition of the index is not on the derivative aspect, but rather on the multiplication aspect. Okay, so this is now how you write down this straightforward notation in terms of an indicial notation. So note that Lig is the Lagrangian finite strain tensor, and similar procedure will lead to your Eulerian finite strain tensor. The only difference that you'll be having a minus sign here simply because we know for a fact that your K, okay, has a 1 minus h there, while J has an f minus 1 there. Okay, so 1 minus h. So the negative sign here, if this will cancel, there will not be any negative sign here. But if this cancels out, there will remain a negative h. That's why this becomes a negative sign. Okay, that's it for the deformation and strain tensors. I'll see you in the next video to continue on the infinitesimal strain tensors. Thank you very much for listening.